Welcome to A2Z Physics and Chemistry. So today we are going to discuss about electrostatic potential, which is very important for the class 12 students. So we know that when an external force does work in bringing a body from one point to another point against a force, then the work is stored in the form of the potential energy. That here the statement is that when an external force does a work against a force means we know the gravitational force, the spring force. These are the different force which are working or in which the force and the work terms are against each other. So again what is that? When an external force does work done in bringing a body from one point to another point, then against a force, just like your gravitational force and the spring force, then the work is stored in the form of the potential energy. But when this external force is removed, then the potential energy get converted into kinetic energy. So in this type of situation, the total kinetic energy, that is the kinetic energy plus the potential energy is constant. So this is called as the principle of conservation. So just like your gravitational force, your electrostatic force are the conservative force. Gravitational force and the electrostatic force, these are the two forces actually called as the conservative force because they depends inversely, they obey inverse square law, or we can say the force are inversely proportional to the square of the distance. And in case of the gravitational force, the mass of the mass due to the potential energy of the gravitational force is equivalent to the charge of the potential energy in case of the electrostatic force. Okay. So now starting with the introduction part of this chapter, let us assume a point. Let us assume a charge which is present at the origin. Now another test charge. Suppose this is small q, and we are bringing this charge from suppose R to P. Again repeating the same. Now let us consider a charge q which is placed at the origin of an origin. Now let us consider another test charge which is moving from R to P. Okay. So in this type of situation, what happens? We have to think about two important law actually, or two important property. The first is that the test charge small q should be very small, so that the configuration due to this small q cannot be disturbed by this capital Q. And the second point is that we have to move the charge from R to this test charge from R to P point. Okay, so these are the 2 points we need to understand for this. Now the important property is that in this case, while transferring the charge from R to P, then we must need an external force which is called as the F external. Okay, and as here there is a positive charge, we can say Q, and here also there is a positive charge small q, then there must be some electrostatic repulsion between them. So this is represented as the effective force Fe. So while in this situation, when we are moving the charge or bringing the charge from point R to P, the external force must counterbalance the electrostatic force minus Fe. So F external should be equal to minus Fe. So in this case, what happens? As we know, the net force will be equal to 0. That means the net acceleration will be equal to 0. That means the speed in bringing the charge will be very slow in this case. So in this case, the work is stored in the form of the potential energy. But as soon as we remove this external force, then the potential energy will be converted to the kinetic energy, and the net force due to this potential and kinetic energy is constant in this case. Okay. So now the work done, or we can say the force will be equal to Q by 4 by epsilon 0. This is r square. Suppose this is r square and this is a unit vector r in this case. Now we know that at every point in the electric field, then there must be a potential energy, and the work done will be increasing in this case. The work done increases the potential energy and by an amount which is the difference between the potential. That is, we can say this WRP will be equal to UP minus UR. Okay. Again repeating the same. In this situation, the work done will be the work done increases the potential energy by an amount which is the difference between the potential. That is UP minus UR. So based on this, we can say two important properties. The first important thing is that this work done, which is called the WRP, it is a conservative force. Conservative force means it does not depend upon the path followed. Rather, it depends upon the initial and the final position of the point charge. Okay. So this WRP in this case is a conservative force. Now the next important thing is that as in the same equation also, we know that the work done never depends upon the potential. Rather, they depends upon the difference between the potential. So this is very important one to describe the potential, or we can now define the potential energy. Suppose we have taken this R point will be at infinity. Suppose the R point is at infinity. Now this will be UP minus Q infinity. But now the potential at the infinity will be equal to 0. So now this is UP. So now we can define the potential energy. The potential energy can be defined by bringing the charge, it is the amount of work done in bringing a charge from infinite to a particular point. The potential energy can be defined as the amount of work done in bringing a charge from infinity to a particular point. This is called as the potential energy. Next, we have to switch about to the actual part, which is called as the electrostatic potential. We know if we are doing some work, that means there must be some force, external force associated with this. As this is the electrostatic potential, then F will be equal to Q into E, because we know that the electric field will be equal to always the force per unit charge. So F will be equal to Q into E. So that means this W, this work done depends directly to the electric field. So what happens? Now we have to take W by Q in one side, because this W by Q represents the characteristic of the electric field. The characteristic of the electric field. So now the amount of work done in bringing a unit positive charge represent the potential at that point. So now we can now write BP minus VR. BP minus VR will be equal to UP minus UR divided by Q. Okay. Actually, what happens here? BP represents the potential at point P, and this R VR represents the potential at point R. And UP and UR are the potential. These are the potential energy at the point P and R. As we know, always V equal to W by Q. Represents the potential at the point P, and VR represents the potential at the point R, and UP and UR are the potential energy at the point P and R. Okay. Now, as we know, V equal to W by Q, we know the potential will be equal to W by Q. In this case, the work done is converted into the potential energy. So now VP minus VR represents the potential difference. Okay. So now we can define this electrostatic potential as the amount of work done in bringing a positive charge from one point to another point, or we can say from infinite to a particular point. This is called as the electrostatic potential. Again, electrostatic potential is the amount of work done in bringing a unit positive charge from one point to another point. Okay. So this was today. If you really like my video, then do subscribe, and thanks for watching my video.